Hey everybody. Sorry for the couple minute delay. I think I told you it's been a while since I've streamed, so I'm still mastering it here. So we'll give everybody a second. Let me make sure that everything looks okay. What happened? I don't know. In regards, are we good? I think we're good. Okay. I think we're okay. Anybody out there? That is the question. Okay, all right. Are we good? Perfect. Oh my goodness. I feel like the old man, the technologically inept old man. I swear I'm not. And so maybe I am. So okay, let's do this. I guess let's go ahead and jump into things. So yesterday we had started this algebra review. I know there's a link to the video or a link to the questions I'm doing somewhere. So I know they exist. You should be able to find them, I think, without too much trouble. And I'm just going to I'm going to keep on keeping on, as they say. So, hey, from Germany. Maybe I may be in Germany next year. We'll see. Um, but okay, let's do this. Let me find my questions on my other page. We were on 15, so we've been solving just a bunch of different equations. So just to refresh you again on what we had done previously, what had we done? Let's do a 2-second recap. So we just talked about solving a bunch of different equations. So I had linear equations. We talked about different ways to solve quadratic equations. And I said I either factor them or use the quadratic formula pretty much exclusively. We talked about the discriminant. We talked about factoring and solving higher degree polynomials. We talked about some absolute value equations. We talked about exponential equations and logarithmic equations. We also talked about some of the important properties of logarithms and exponentials. And I think in a nutshell, that is what we did yesterday. So as a quick recap. So I'm going to, again, just keep on, I'm going to keep doing this. And it looks like the next three questions, 15, 16, and 17, are all going to be rational equations. And these typically, rational equations, rational inequalities, can be a little more work. So again, it looks like there's a decent little delay between me talking and what I'm seeing appear. I think it's for whatever reason. So my apologies if you do ask a question and it feels like I'm answering slowly. So, okay. So again, the idea is when I look at this, again, you're trying to classify things. I always tell people it's like a biology class, right? You have the genus, the phylum, all those things that I don't remember. But you classify them, right, because they have things in common. And you want to be able to classify different types of equations and inequalities because, again, there's often a set of techniques developed to solve those. So this is going to be a rational equation. And the thing that I'm looking for that makes it a rational equation is I'm looking for variables to whole numbers, or whole powers, 1, 2, 3, 4, but I want them to appear in the denominator. Well, I've got one right there. That's going to, and again, the rest of it is just numbers. So I'm being a little sloppy here, but that is what I'm basically looking for to see a rational equation. So I want to solve this thing. And typically what I try to do, my idea, is I try to get rid of the denominators. I try to get rid of the denominators by using the least common multiple. And if we go back to one of my very early questions, we had this linear equation, number 2, and I said, hey, to simplify that, there's a couple different ways, but I multiplied by the least common multiple of those denominators. Well, guess what? There was a reason that number 2 was there. There was a reason I talked about multiplying by the least common multiple of the denominators. And it is because that is a very, very nice way to solve rational equations. So, same idea. We're just going to get rid of the denominators. Okay, in this case, we'll get a new equation, basically depending on what's in the numerators and in the denominators, and we'll just see what happens. Okay, so I'm looking at the denominators. What do we got? I've got an x, I've got a 2, and you could think about, well, this is, if I can do it, that's really just 5 over 1, right? So that's the denominator, so I'm just kind of neglecting that. So the least common multiple, the thing that I'm going to multiply both sides of my fraction by, I'm going to multiply by 2x. So I'll give myself a little space on the right, because I know I'm going to multiply. So I'm going to multiply on the left by 2x, and I'm going to multiply on the right by 2x. Okie dokie, I've got to distribute that 2x to both things. I don't know if it's worth writing it out. Maybe I will write it out once, and then I'm going to I'm going to stop doing it. So if you distribute, we would have 2x over x plus 2x over 2. And again, you can think about this as being 2x over 1. And on the right side, 5 times 2x is simply going to be 10x. Well, if we simplify on the left side, the x's will cancel, the 2's will cancel. So I've got 2 plus x. I feel like, did I leave something out here? I think we're okay. 2 plus x equals 10x. Well, now all I have to do is, I've just got a linear equation. I can subtract x from both sides. So I have 2 equals 9x. And if I divide both sides by 9, I'm going to get my solution of x equals 2/9. And of course, you could always go back and check that that is correct. And hopefully, that is correct, because you'll get 9/2 plus a half, which is going to be 5. Okay, so hey, that looks good. So all we're doing is just getting rid of denominators. And notice, okay, so this is kind of the $64 question. When I distributed and I got rid of denominators and I sort of looked at what was left over, well, in this case, I ended up with a nice linear equation. Numerator is x, not 1. Is it? Did I leave one of them out? Thank you if I did. You are correct. Okay, thanks. Okay, well, let's do that one. So, okay, well, hey, that's 15. We'll put a little star here. Thank you so much. I did copy it down incorrectly. So 1 over x plus x over 2. Okay, but, so this is good. Thank you so much. Because we're still going to start it in the same way. So maybe this is kind of, you know, useful. So I would still multiply both sides by 2 over, by 2x. I'm still going to do the exact same thing that I started with. Still multiply by 2x. On the left side, when I distribute, 2x times 1 over x is still going to be 2. Now, when I distribute to the next term, the 2's would cancel. I would have x times x. So that's going to leave me with x squared, and still 10x on the right. So again, notice the distinction. Thank you so much, Queen Bee. I've got an x squared instead of an x because I copied the question down incorrectly, and I left the x out. Okay. So in my first one, I said, oh, well, that's linear. We know how to solve it. Great. I do the same thing now. I just think, well, what is this? What type of equation is this? And how do I solve these types of equations? Well, this is going to be a quadratic equation because I see that x squared term in there. And we know how to solve quadratics. We talked about this yesterday. We said we make one side equal to 0. And I'm going to do a couple steps at once. So I'm going to make the right side equal to 0 by subtracting 10x from both sides. And then I'm going to write it in descending power. So there's my x squared on the left side. I'm leaving that alone. I'm going to subtract 10x from both sides. And there's my plus 2 that was already on the left side. Well, if I subtract also 10x from the right side, again, that's going to give me 0. And that's why we're subtracting 10x, because we said we want 0 on one side. Okay, this is now a quadratic, I think, factor or quadratic formula. You can try to factor this. This is not going to factor nicely. So I'm going to just use the quadratic formula. Yeehaw. I'm not going to write down the quadratic formula because we did talk about it yesterday. So it says we get x equals negative of the b value. Well, sounded a little country there. My b value is going to be negative 10. So negative b plus or minus the square root of b squared minus 4 times a. And again, the a is whatever number's in front of x squared, which is a 1. And then we multiply that by c, which is the value of our constant, which is 2. And this is all over 2 times a. Okay, we're having fun. I don't know how much of this I'll go through. I'll do a little bit. So negative of negative 10 is going to be positive 10, plus or minus the square root. So you can check my arithmetic here. Negative 10 squared, that's negative 10 times negative 10. That's going to be 100. That'll be 100 minus 8. 100 minus 8, well, that's going to leave me with 92 over 2. And I'll let you simplify this down. You could write this as 10 over 2 plus or minus the square root of 92 over 2, which is going to be 5 plus or minus, let's see, the square root of 92, that's what, 2 times? So 4 is going to go into that. So you can certainly start reducing the square root of 92. I will leave that to you. So notice you could simplify this a little further. Let me know. Oh no. Let me know if. Let me know if you need to see the square root of 92 simplified. Otherwise, again, you could write that, say, as what? 4 times 23. So you could, well, geez, okay, I always do this. I'll say I'll let you do it, and then I start talking about it, and then I do it. So you could write the square root of 92 as 4 times the square root of 23. That looks okay. And you could put the square root of 4 as a 2. You would still have the square root of 23. This would all be over that original 2. So we could cancel. So it looks like we would actually be left with 5 plus or minus the square root of 23 is my solution. Oh my goodness. Okay, thanks, Queen Bee. That's the problem with the delay. By the time you answer, it's too late. So, but okay, well, for completeness' sake, it doesn't hurt. But again, it's the exact same idea, right? It's just once the denominators are gone on a rational equation, that's when I just sort of stop and regroup. I say, aha, the rational part is done. What have I got now? One thing I should absolutely mention, with rational equations, it's very, in general, check your solutions when you deal with rational equations. So do check that both of these will, in fact, satisfy this original. Mainly what you need to look out for is somehow magically a number turning your original equation into something undefined. Like, for example, if we got a solution of x equals 0, I would say, oh, that can't work because that would make, we would get 1 over 0, which is undefined. So do check. Okay, let's go through these other ones a little faster. Again, the devil's in the details. But again, hey, if it's rational, this is how you get started. That's half the battle. Okay, so this is a nice rational equation. Again, I see this x to the first power in the denominator plus 1. I'm going to do the same thing. I think, well, how could I get rid of that denominator? What could I multiply both sides by? Well, you can multiply both sides by the denominator of x plus 1. So that's simply what I'm going to multiply both sides. Oh, hey, Rosalind. I didn't realize that was you. Okay, welcome back. I was sitting here. I was like, "Where's Rosalind?" Like I was sitting here honestly, like I felt a little bad. So I feel better. Okay, so same thing here. We're just distributing. So I'm just multiplying by this denominator of x plus 1. Now notice on the right side, okay, so on the left side, the x plus 1 cancel out. That's why we did it. You're left with 2x minus 1. It's not necessary to write the step. You could put the 3 up front if that makes you happy, just because it looks, it looks more familiar. Maybe you see it a little bit better when you go to distribute. So this is 2x minus 1. On the right side, we have 3x plus 3. And I say, aha, well, this is just linear. So I could subtract 2x from both sides. So that's negative 1 equals x plus 3. We could then subtract 3. That's negative 4 equals x. And again, you could go back and check and make sure that that value, in fact, is a solution. So that should be good. Same idea, getting rid of denominators. I'm going to go through these because I know least common denominator. Yes, that sounds lovely to me. Yeah, multiply by the least. You're multiplying by the least common multiple of the denominators, which produces the least common denominator, I guess would be the technical way of saying it. But yeah, yes. If you said that to someone else, it's correct, and which is the important part. But yeah, I would say I know exactly what you're talking about. So yeah, and even me sometimes I'm like, am I saying it correctly? So it is something, right? We all want to get correct. I'm going to move down for 17 because I think this one's going to turn out to be a little bit long. Okay, so again, it's the exact same idea to get started. Let's multiply by something to get rid of the denominators. And then we just play with what's left. It's just like what's left. Okay, so, well, I've got the denominators. So my denominators, right, I see an x. I see this x minus 1. And then, okay, again, the denominator of the 4 is a 1. So I'm just going to leave it gone. In general, if you want to, you can always just, whatever the denominators are, just multiply both sides by that stuff. It will cancel out. It may be, if you don't do it efficiently, you may get a little extra, but you can simplify it later. Okay, so this one's just going to be longer because I'm multiplying both sides by, quote unquote, more stuff. So I'm going to multiply both sides by both x and by x minus 1. Because when I distribute to the first term, the x's will cancel. And when I distribute that, all of that to the second term, right, the x minus 1s are going to cancel. And that's what I want. So if I do that to the left, I have to do it to the right. So there's x times x minus 1. I've got an extra set of parentheses on the left. It really doesn't matter. It's all correct. Okay, and again, now it's just being careful with the algebra. So I'm distributing all of this stuff to the first term and to the second term. And really all I'm thinking is just jot everything down, and except for the stuff that cancels. So when I distribute to the first term, again, the x and the x are going to cancel. So I would be left with 3 multiplied by, it looks like x minus 1. There's my minus sign. So there's my minus sign. And when I distribute to the second term, the x minus 1 and the x minus 1 would cancel. And that would just leave me with minus 5x. And on the right side, okay, again, we're going to be able to start simplifying. Hey, good afternoon there. So I could write that. I could take the x and the 4 and make that 4x, and then have x minus 1 on the right. Okay, if I distribute some more on the left, 3, we would have 3 times x, minus 3, minus 5x. And on the right side, if we distribute, we would have 4x squared minus 4x. And again, let me know if you all see something incorrect. So I'm staring too and making sure I'm not doing anything too crazy. Okay, so I think this looks okay. So on the left side, I've got negative 3. I've got 3x minus 5x. Well, that is going to be, negative 2x. And I've got 4x squared minus 4x. And we could have stopped and made this observation at this step or at this step or at this step. And that observation is, again, what type of equation do we have and how do we go about solving it? Well, even here I can look at this and say if I distribute it, basically I'm thinking if I distribute all that stuff out, I'm going to get something that looks like that bottom line. And something that looks like that bottom line is going to be quadratic. So again, you're just back to like something previous. And this is so common, right? You just sort of keep using earlier stuff. Jarrett, my apologies. You asked what software did I use, and I didn't answer because I was so I'm using an iPad Pro. I'm just using an iPad, and there's an app called Notability. There's two popular apps. There's Notability, and there's another one. I forget the name of it, but they're pretty comparable, and it's very inexpensive. So that's all I'm using, and just a stylus, So, okay. Anyways, back to stuff. I don't know, you all tell me, should I go all the way through this? So this is a quadratic. Whatever, I always look at my squared term. I like the coefficient on that to be positive. So on the right side, it's already positive 4x squared. I like that. So I'm going to make the left side equal to 0 because I don't want to move that 4x squared over. I like that. So I'm going to do two things. I'm going to add 2x to both sides. And I'm going to add 3 to both sides. So we'll do a couple things at once. So on the left side, I'm going to get 0. And on the right side, I've got 4x squared. Negative 4x plus 2x is going to be minus 2x plus 3. So that's where I'm at now. And again, I don't think I'm going to grind all the way through this one. By all means, in the comments, say work it if you want me to. What I would now do is, again, I would just use the quadratic formula. This is a quadratic. It's a quadratic with my a value equal to positive 4, my b value equal to negative 2, and my c value equal to negative 3. Why negative 2x? Did I mess up? Well, if you've got negative 4x and you add 2x's, wouldn't you still have negative 2x's? Is that correct? Right, so negative 4. If you've got negative 4 of something, if you've got negative $4 in the bank and I give you $2, right, you're still negative $2 in the bank. So I think my algebra here is okay. Double check that. Okay, so you said since the leading coefficient is not 1, use the formula. I agree with you. That's what I would do. And if I remember correctly, this one doesn't even factor. So, so you would have x equals negative b plus or minus the square root of b squared minus 4 times a times c. Did I do something wrong? Because this is going to say no solutions. So check my arithmetic here. Does everything look good? So this to me, negative b squared minus 4 times a times c. Notice this discriminant. If my math is right, whoops. If my arithmetic is right, and I think I am okay, notice this discriminant is going to be negative. Whoops. This discriminant is going to be negative because negative 2 squared minus 4 times 3 is going to be a negative number. So that simply means this has no solutions. So this quadratic equation has no solutions. And what that means is this original one also has no solutions. So assuming I didn't make an algebra mistake, that's what it simply tells us. And well, it's okay. It's possible for equations to not have solutions. I'm trying to think. Is there something clearly right or wrong about that? But okay, let's just assume it's right. Why not? Okay. So that is the gist. 15, 16, 17 are just rational equations. You get rid of the denominators, you look what's left. I would say typically in through calculus, you're not going to see something, it's going to give you typically a polynomial, I think, for a lot of stuff. And it's going to give you something you should be able to, air quotes, something you should be able to solve. You being the proverbial you, whoever's out there listening. All right, so 18, you all tell me too when you've had enough. Again, there's no way I'm going to get through this. I'm probably just going to start, since tomorrow's Monday, I'm just going to, I think I'm going to start doing stuff in the evening, maybe around 6 my time. Hopefully people are off work, out of school, and so I'm just going to keep going through it. Okay, so with the next bunch of questions are all inequalities. Inequalities you have to be much more careful with. You have to be much more careful solving inequalities. You have to be much more careful when dealing with inequalities than you do compared to equations. There's more things you have to check. They're more tedious. The exception to that is linear ones are still pretty straightforward. Also remember, if you multiply or divide by a negative number, only if you multiply or divide by a negative number, remember that the sign on an inequality changes. So that's sort of the important algebra thing to remember. But otherwise, it's, life as usual. So to me, in my head, when I'm looking at this, right, I'm almost thinking, forget about the inequality. What if it was an equation? How would I solve that? Well, that's linear. I would subtract 4, and then I would divide by 2. Well, guess what? You do the same thing here. There's nothing different about it. So I could still subtract 4. Negative 11 minus 4 is negative 15. And if you divide both sides by 2, well, I'm dividing by a positive number, so the inequality doesn't change directions. So negative 15 over 2 would be the solution. Maybe I'll start it early then, Rosalind. I can start it at 5:30. I'm not a night person so much, so maybe I'll just start it earlier. So, okay, that is our solution. It says that x has to be less than negative 15 over 2. I'm just going to make a number line. Remember, if it's not equal to, we put an open circle to indicate that we don't use that point. So, okay, open circle. Where is less than? Less than is to the left. Typically, at least again in a calculus course, you're going to use interval notation. So we could say, the way that we could describe this interval, so x less than negative 15 over 2, which we've also shaded, we would say that's from negative infinity up to negative 15 over 2, again, parentheses. So parentheses, we don't include the value, and recall if we use brackets, we do include it. And typically, again, you'll see both of them, but interval notation is, I would say, more common. All right. 18, so no big deal, easy peasy. That's just like a linear equation. Hey, just remember to be careful to flip the inequality if you multiply or divide by a negative number. Okay, so 19, 20, 21's linear, so we'll not that one. 19, 20, 22, 23, 24, 25, 20. So a lot of the remaining problems, we're going to do the same thing. And typically what you do for an inequality is you make one side 0. If you have fractions, you'll figure out what makes the numerator 0. You'll figure out what makes the denominator 0. We're going to put those on a number line, and then we're going to start testing points, is what we're going to do. Yes, so you're already factoring there, Rosalind. Perfect. So in my head again, I'm still thinking, I'm thinking about solving x squared plus 6x plus 8. That's really what I'm doing. And just like Rosalind said, old Queenie there, our friend, I think you can factor here by using 4 and 2. And we can use 4 and 2, right, because we need two numbers that multiply to positive 8 that add up to positive 6. 4 and 2 does that, so that's x and x. Well, we said we set each of those equal to 0. And my first one would give me a solution of -4, and my second one would give me a solution of -2. Okay, so those are the solutions to the quadratic equation, not the inequality, right? We want the inequality. We don't want the equation, but, well, guess what? The equation gives us useful information. What about set notation? If you wanted set notation, you would just write it's the set of x such that x is less than -15/2. That would be set notation. So that's set notation. I can't remember ever seeing that hardly. You hardly ever, at least me, at least personally, hardly ever saw it in calculus. Okay, so that was a separate question that someone asked in the chat. Okay, let's get back to this one. So we're trying to solve this inequality. Well, these points are useful. Can you review using zeros to write a polynomial function? Keep that in mind, Justin. I don't know if it's on this review sheet that I'm doing, but if you're present, if you happen to be floating around, yes, the answer is yes. I would be happy to do that at some point. So what I do is I look at the numbers that make it 0. And if you have a fraction, you'll look at what makes the numerator 0 and what makes the denominator 0. There you're finding where it's 0 and undefined. Those are still important points. Okay, so there's -4 and there's -2. Now, what this does is, the one thing I can already say is that -4 and -2 are not solutions to the inequality. And that's going to be, that makes sense, right? Because it says if we plug -4 in for x, or if we plug -2 in for x, we get 0 out. I mean, that's what we just found by taking that equation and setting it equal to 0, right? What values of x are going to spit out 0 at the end? Well, if you plug -4 in, or if you plug -2 in, you're going to get 0 out at the end. Well, 0 is certainly not less than 0. So already I know that -4 and -2, those two values don't work. So I'm going to go ahead and put two big open circles there. And now this is where you have to just test points, and this is where it gets annoying. So I've got three intervals, right? I've got numbers less than -4. I've got numbers in between -4 and -2. And then I've got stuff bigger than -2. What you have to do is just take a number from each one of those intervals, plug it back into your inequality, and think, does it work? Do I get something less than 0? Because that's what we want. We want values at the end of the day that are less than 0. That's good. Well, you can take any point from that interval. So I'm going to test, let's say from this first interval, something less than -4. I'm going to use x equals, you may say -5. I'm going to use -10, just because a lot of times that makes the arithmetic, for me, easier. So again, I'm plugging it back into x squared plus 6x plus 8. So let me maybe jot this down. So we're testing x squared plus 6x plus 8, and we're really asking ourselves, do we get something less than 0? Well, -10 squared plus 6 times -10 plus 8. Is that going to be less than 0 is the question. And I think no, because -10 squared is going to be 100. And then 100 minus 60 plus 8, that doesn't work. So what that means is numbers less than -4, none of those are going to satisfy that inequality. And if, say, we test, let's say x equals -3, right? -3 would fall in that middle interval. So then I'm thinking, is -3 squared plus 6 times -3 plus 8, hey, is that less than 0? And that's going to be 9 minus 18 plus 8. That is going to be less than 0. Let me change that. That is going to be less than 0. So that means the numbers in between -4 and -2 work. So I'm going to go ahead and shade those in. And last but not least, you could test something larger than -2. I would use 0 because, again, it makes the arithmetic easy. And if you plug 0 in for x, right, if you plug 0 in for x, you're going to get 8 on the left. 8 is not less than 0. So I know that those values won't work either. So in this case, we could say that our solution set is going to be those numbers that I shaded in between -4 and -2, but not including those numbers. So that would be my answer. And again, it makes sense too if you think about graphing. You know, if you think about the graph of x squared plus 6x plus 8, that's going to be a parabola that opens upwards. And what we did by setting it equal to 0 was we found the x-intercepts. We found -4 and -2. So we found where it crosses the x-axis. And at -3, that's where the vertex is going to be. I don't know the y value. I don't really care for this question. But my parabola would look something like that. So again, if you look at the graph and you think, well, if you look at it in the graph, where are the y values negative? Where are they below the x-axis? Well, it's between -4 and -2. So that all kind of jives, right? It all syncs up. If you wanted to do set notation, it's the same thing. You could just say it's a set of x. Sometimes they'll put a little colon such that. I always like the little such that. You could say -4 is less than x is less than -2. And again, those little brackets on the end, that is, right, set notation for those of you that may not remember. The bracket has to do with a set, a collection of objects. So here are a collection of objects. It's those numbers between -4 and -2. That's it. Should circles be open? Yes, for sure. Your circles should be open. And you can see I tried to make mine pretty open in my picture, right? If I was going to shade them in, right, that's what my shaded in circle would look like on the left side. So yes, my circles should definitely be open because if you have less than or greater than, it's going to be open because you're not including those values. If it's less than and equal to or greater than and equal to, right, the equal to means we can use it. So then you would shade it in. Okay. 340. You all, oh, in the graph. Okay, I see what you're saying. So, good point. I was actually interested in this. Yes, in the graph, they should absolutely be shaded because my quadratic goes through those 2 points. So kind of think about it as being a separate question in a way. Somebody just said, you know, hey, Patrick, forget about solving that inequality. Somebody said, hey, Patrick, graph y equals x squared plus 6x plus 8. I say, okie dokie. And I can make a t-chart, or I could find x and y intercepts, and I would get that graph, that parabola. And I would say that's the graph. -4 should be shaded in because -4, 0 is a point on the graph. -2, 0 is also a point on the graph. But if I wanted to think, you know, where are the y values negative, well, I would know I would need to go below because where they are shaded in, that's where it's equal to 0. So it wouldn't satisfy that inequality. So again, from that graph, I could immediately still arrive at that same solution. And that graph that gave me that same solution also coincides with that solution set, right? So the numbers that work for that inequality are those numbers we shaded on the number line. That's correct. But this is also the correct graph of the function. So very minor distinction. It's kind of like you have to kind of keep in mind, what are we doing? Are we making a graph, or are we shading numbers that satisfy an inequality? And those are two separate, two very separate questions. You can use the graph to answer it, but okay. Number 19. I know it's Sunday. Again, you all tell me, say, I think mainly you, Rosalind. You tell me. You're my person helping me here. So you let me know, and we'll call it a day. So number 20, x to the 4th minus 4x to the 3rd minus 21x squared greater than 0. This may look familiar because we actually we did this one yesterday, right? This was one of the equations I solved, one of the polynomial equations that I solved. And we're going to do the same thing, though, and that's the point why it's in there. So I said to solve this. So again, I'm still thinking about it as being an inequality. Or excuse me, I'm thinking about, like, what would I do if it were an equation? I will, though, just leave it as an inequality. So I would factor out my x squared. I would have x squared minus 4x minus 21. If I factor the left side, so I'm factoring out that smallest power of x. And then notice what's inside the parentheses. That's still a quadratic that I think factors. And I think we could use x minus 7 and x plus 3. I think that's how it would factor. And again, we did this yesterday, which is why I'm going through this part just a little bit quicker. Now, again, suppose it did say equal to 0. I'm going to do the same thing. I'm going to make my number line. If it was equal to 0, what would my solutions be? Well, I would take x squared and set it equal to 0. And that would give me x equals 0 as a solution. If I take x minus 7 and set it equal to 0, I would get x equals, well, positive 7. And if I take x plus 3 and set it equal to 0, I would get x equals negative 3. All right, so I'm just thinking about it as being an equation and solving. And then I'm putting all those numbers on a number line. So I'm doing the same thing before. I'm thinking, hey, if it was an equation, what are the solutions? Put those solutions on a number line. That's what I'm doing. Well, what did we do in the last one? After we had the number line, we thought, well, did those values satisfy the original inequality? And notice negative 3, 0, or 7, all of those are going to give you 0. 0 is not greater than 0, just like the last question. We had less than in that case, but again, so negative 3 won't work, 0 won't work, 7 won't work. Well, what do, Patrick? We do the same thing. It's fun, because now we have 4 intervals instead of 3. So I'm going to go through maybe one of these, and then I'll let you, kind viewer, go through the other ones. So in this case, notice my 3 points are going to give me 4 intervals. Yeah, so we're just testing points. So, oops, I wrote x equals 10. I meant x equals negative 10. Let me clean that up. I think I said it. Hopefully I said it. So x equals negative 10. And then I'm using x equals negative 1. That falls in that next interval. X equals positive 1 falls in that middle, or that next interval, I should say. And then in the last one, we can use x equals 10. So notice, for example, suppose I check the middle interval, or excuse me, that third interval. I'll check x equals 1 because it's easy. You could go anywhere. You could go where it's factored. You could go back to the original one. So if I go back to the original, I would have, well, 1 to the 4th power minus 4 times 1 to the 3rd power minus 21 times 1 squared. And I'm thinking, is that greater than 0? If I replace all that. Well, this is going to be 1 minus 4 minus 21. Is that greater than 0? No, 1 minus 4 is negative 3 minus 21 is going to be negative 24. which is certainly not greater than 0. So you basically would not shade, right? So you wouldn't shade that interval from 0 to 7. So I know 0 and 7 is not going to be in my solution set. And then you would also have to test, I would also have to test the other points I used. I would also have to test x equals -10. I would, again, plug it back into my inequality. I'm going to plug in -10, do the arithmetic, and I'm going to say, is it greater than 0? If it is, I shade it in and say those values are good. If it's not, like in what we did just now, I would say we don't use those values. I would also have to test, for me, I would have to test x equals -1, and then I also picked x equals +10. So I would then have to test those remaining values. Greater than 7 is true. Okay, that sounds good. So Rosalind says that one works, and that one absolutely makes sense to me. So I know that that's going to be part of my solution set. So I don't know all of it, but I know from 10 to infinity is going to work. So I know that 10 to infinity is going to work. Now the interesting thing is I could actually get the solutions because I know with this graph, x to the 4th minus 4x to the 3rd minus 21x squared. You may remember from algebra, right? X squared looks like that. Well, it's going to turn out x to the 4th also looks like that, and so does x to the 6th, and so does x to the 8th, roughly like that. Now, the thing is, in the middle, anything can sort of happen. They call it, we call it the end behavior. So if I were to graph, say, this original x to the 4th, so if I were to graph y equals x to the 4th minus 4x to the 3rd minus 21x squared, if I were to graph that, I would know on the ends it's going up. Now, sort of what it does in the middle is a little bit of a mystery, but I know that on the ends it has to go up really big, which means it's going to be greater than 0. So it should automatically work here. That makes sense. And it shouldn't work for the middle ones, right? So it looks like the solution set should be the first interval from -infinity up to, and also be careful. Sorry, somebody's yelling in my house. Don't mix up your test points with the intervals. That would be an easy thing to make a mistake. I almost did it here. So notice my interval would be from -infinity. Let me keep my same colors here. From -infinity up to, we tested x equals -10, but I don't care. The value we go up to is -3. And then we skip everything else until we get to 10. What we'll do is we'll write, it looks like a U, that's the union symbol, and that would be my solution. I could actually, I could not do the interval in this case, honestly, because if you know that x to the 4th increases on the ends like I do, like I said, it has to do. So it's got to cross at, what do we say, at a -3. And then it hits 0 again. The interesting thing is, because this has multiplicity 2, what it does in terms of the graph, it bounces off of that. It doesn't cross. And then it would go up to 7, and then it would keep on trucking. So this is actually interesting. It goes to show if you know about graphs, you could also do this without all this plotting points. And if you haven't seen this type of stuff about multiplicity and how that affects the shape of a graph, you should see it in Algebra 2, and if it's not in Algebra 2, then in a pre-calculus course. It's not really heavily discussed. Say when you get to calculus, they're not going to say, oh, hey, it's got multiplicity 2, don't forget it doesn't pass through. And it could have been on the top as well. It basically just doesn't cross through. So it's kind of interesting, I think. Well, it isn't. And it makes sense if you think about it, why it does that. if you stop. It's like, why would it bounce off if it's that 0, it has an even multiplicity, is what we would say. It makes sense. Think about it. Okie dokie. 21's quite simple because it's just a couple different linear inequalities. And we would solve this, again, much like the linear one that we did yesterday, the equation. So I'm going to have 4x is greater than 2x plus 1. And then I'm going to take 2x plus 1 is less than 3x plus 2. And, okay, these are both linear. Let's just solve them. Nothing crazy. Should be 7. Should it be 7 to infinity? What'd I say? 10c? See? Ugh, thank you. Thank you. I even said, right, be careful. Don't accidentally use your test points as the interval. And then I exactly did it on that point. Thank you. See? I'm even telling you not to do it. And I did it. So, perfect. Does that look good? I think that should look good. Okay. That's where I say, oh, I was making sure you're paying attention. Yes, 7 to infinity. Perfect. Thank you so much. Okay. So this is just linear. So I'm going to go through this one a little quicker. So if I subtract 2x, 4x minus 2x, I would have 2x less than 1. I divide by 2, divide by 2. This says x is less than 1/2. Now we have to be careful because this is a compound inequality. So we have to sort of satisfy everything. So I already know to satisfy this sort of left chunk, only values less than 1/2 are going to work. Well, let's look at this other part. So I can subtract 2x. So that's 1 less than x plus 2. Then I can subtract 2, subtract 2. It says x has to be greater than -1. So both of these have to be satisfied. It has to make that inequality happy, and it has to make that other inequality happy. So x must satisfy both. And well, again, this is where I like to use an inequality, or a number line rather. So there's 1/2. There's -1. So for the first one, right, it says x has to be less than 1/2, which would be everything to the left of that. That's less than. And then if we look at everything where x is greater than -1, well, again, I would have an open circle, and I would shade, to the right. But if you look at the overlap, right, the overlap is going to be right there in the middle. That's going to be the solution. So we would say it's got to be larger than -1 and up to 1/2. That would be my notation. So none of my inequalities have equal to's. I think when I was using this, I was just using Microsoft Word, and to include an equal to sign, you have to like go and find the math symbol and da-da-da, and it was very annoying. And less than and greater than are just right there on the keyboard. So, all right, so that's number 21. 22 is honestly probably an easier version than a lot of these. And 23 is already even set up for us. I probably should have done 23 and then 22 and then these other ones. So 22 is the same thing. So I guess let me ask real quick. X cubed greater than x. How would you solve this? And I guess Queen Bee, that goes to you because there's no one else. Phaser's there too. Okay, so I got two people. How should we solve x to the third greater than x? Does anybody have an idea? This is where if I was in class, I would just stare at you. Anybody? Anybody? Nobody? All right. So I hear subtract x, and set it to 0. So you're both saying the same thing. Okay, I like Queen Bee. What about Well, how about before that, what if let's divide both sides by x. So x to the third divided by x, that's x squared on the left. And x divided by x on the right, that's 1. Because that's easier, right? That looks nice. To me, x squared greater than 1, that looks better than x to the third greater than x. Does that work? Is that okay? Is that legal? So I agree. Okay, so I have no complaints about x to the third minus x greater than 0. I am right there with you. I agree with x to the third minus x greater than 0, factoring out an x, like I said, 100%. I no qualms. My question is, can I do what I did on the right to make it easier? And then I could say, I could subtract 1. Because now I could say, I would rather deal with this, right? If it's okay, I would much rather have x squared minus 1 greater than 0 than x to the third minus x greater than 0. I mean, it just visually, right? The left one looks a little more tricky, and there's probably more. Okay. So calculus here, which is maybe we shouldn't be surprised that calculus is giving us some pearls of wisdom. You cannot do this. This is, so don't do this. No, 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 no. This is algebraically incorrect. What you're going to do, like people are saying, they're saying you need one more 0, you need one more root. You're going to throw out some important information by doing that. So, and it's much like, you can think about it this way too. Suppose I was going to solve, x squared equals x. Right? You could subtract x from both sides. You could factor out x. And you would get 2 solutions. We would have x equals 0 and x equals 1. And those both look nice. But equivalently, right, if we divide both sides by x, we're only going to get the solution x equals 1. We're missing this solution of 0. And that kind of makes sense because, right, if you're dividing by x, you're saying you're dividing by something that is legal to do. So this sort of says we're dividing by something that's not 0 because it doesn't even make sense to do that. So we're throwing this value out, so we have to be careful. Okay, so again, that's long-winded, but the reason why I wanted to spend a moment is because people do this all the time. I said at the beginning, people fail their calculus course because of algebra. It's because they do something like this algebraically, and it feels as natural as a baby's smile, right? It feels like something like reasonable to do if you're just sort of going through it. Okay, x to the third minus x. We factor out an x. That's x squared minus 1. And again, I just think, can I keep factoring? Well, x squared minus 1. X squared minus 1 is the same. We can factor that as x minus 1 and x plus 1. Recall that's a difference of perfect squares, right? X squared minus 1, we say that's a difference of perfect squares. That factors. And I'm going to go through it. Notice if I take the first part and set it equal to 0, that would give me 0. If I take the second factor and set it equal to 0, I would get 1. And the last one would give me negative 1. None of those values are going to work, right? Again, because of the other thing. Because the inequality it doesn't include the equal to part. Again, if you have a greater than or if you have a less than, you're getting 0, right? And 0 is not greater than 0, 0 is not less than 0. So those values never work. And again, just test. So maybe I'll take one value. Maybe I'll test, let's test x equals negative 1/2. So I'm taking negative 1/2 to the third power, and you can look at it anywhere. You can look at it at the beginning. Negative 1/2 to the third power, is that greater than negative 1/2? That's what I'm asking myself. And I think the answer is, what is the answer? I think the answer is yes, right? Because we would have negative 1/8 on the left, and that is greater than negative 1/2. So, right, be careful. Think about a number line, right? Negative 1/2's over here, here's 0. Negative 1/8 would be over there. So negative 1/8 is bigger. So if I go to write my solution, I know that negative 1 to 0 is going to be at least part of the solution. Why are the endpoints not always the same as the intervals? Why are the endpoints not always? I don't think I quite understand your question. So the endpoints are helping me determine the intervals for sure. Yeah, why are the endpoints not always the same as the intervals? So again, the reason why we don't include the endpoints, for example, right, if maybe you're asking something like this, why is that not correct? And I hope I'm understanding it correctly. I'm trying to guess here. Notice if you plugged in, for example, negative 1, right, we would end up with we would end up asking ourselves, is negative 1 greater than negative 1? And it's definitely not. So that's why I keep that open to indicate that we don't use it. So I'm not sure if I'm understanding your question, but hopefully I am. Okay. And then you could do the same thing. So you all tell me real quick, you could test something smaller than negative 1, something between 0 and 1, and then something larger than 1. So, and that would be your solution. So if that feels okay, I'm going to keep going. And calculus 1, 2, 3. I appreciate the kind words. Just keep them coming. You just hang out there and just keep laying it on. No, I'm joking. I really do appreciate it. It's why I keep coming back. So, like I said, maybe I should have done number 23 at the very beginning because it really kind of gives the idea, right, of what we should be doing through all of this. So, my apologies. Okay, so again, if you imagine this being equal to 0 instead, right, I would think, well, it's already factored, so I can get my solutions really easily, so that's nice. I don't really have to, right, I don't have to do all this factoring like I did previously. It's already there. So if I set the first factor equal to 0, I'll get 1. The second one will give me 2. The third one would give me 3. I know none of those work. And again, now you just got 4 intervals to test. So maybe I'll test the first interval. So I could take a point, right, x equals 0 falls in there. So if I test x equals 0, and again, I'm just going to plug it in, I'm going to think, well, notice if I plug in 0, I'll have negative 1. 0 minus 2 is negative 2. 0 minus 3 is negative 3. Is that less than 0? I don't even really care about the values. I know it's going to be negative, right? A negative times a negative times a negative is a negative. A negative is certainly less than 0. That works. Apple, I see your question. 1 second. So I know the solution. I know from negative infinity to 0 is going to be included. And I'm sure there's some other stuff as well. So I'll let you think about that. Again, you could test the next interval and the next interval and the next interval. Okay, so you asked, can we use the cube root? So I assume you're going back to this question, x to the third greater than x. No. The short answer is no, you couldn't use a cube root. Even if it was an equation, using a cube root to me wouldn't make it better. It wouldn't make it, if it was an equation, I would do the exact same thing. And this is what you do almost really, I always tell people, if you're not sure how to approach an equation or an inequality, you a lot of times when in doubt, make one side 0 and start factoring. At least when you have something that's a polynomial. x to the first, x to the second, x to the 10th, x to the 23rd, x to whole numbers. But yeah, in this case, a cube root, even here, say if we took the cube root of both sides, we would get, this, which I'm like, well, what do I do with that now? So yeah, exactly. It won't be. And this is kind of the question you have to ask yourself too, because when you're doing algebra, you can be doing something that's algebraically correct. I mean, you're transforming it into something that's equivalent and correct. The question you have to ask yourself is that new equivalent correct thing useful? And sometimes it is, and sometimes it's not. So it's again, it's a tool, right? It's like sometimes you go get the hammer and you bang and it works, and you're like, all right. And other times the hammer doesn't work, and you put it away and you go get something else. So, okay. This one we could, but I'm still going to go ahead and do it just for sort of consistency's sake. You and me both rig. So I've got this. So before we had rational equations, guess what this is called? So this is going to be simply a rational inequality. And again, a rational equation or a rational expression, it's when you got a polynomial on top and a polynomial in the denominator. A polynomial could just be a constant, 1, 2, 3, doesn't matter. Here we've got a linear expression divided by a linear expression. So for these, typically what I do, same thing. I make one side equal to 0, yeah, so make one side 0. So this is going to be my recipe. Make one side 0, write as a single fraction. So I'm going to do that by getting common denominators. And then we'll set both the numerator and the denominator equal to 0. And how about maybe I'll do this one, maybe one more, and then we'll call it, because I know this has to get to be a little bit long for those of you all watching. Okay, so that's the first thing, yeah. So again, notice this is the same idea. We're doing in a lot of things. We just make one side equal to 0, and then, we go from there. Okay, so 2x minus 1 divided by x plus 1 minus 3 greater than 0. Yeah, so now we're going to get common denominators. So I could write this as minus 3 over 1. Well, I could multiply top and bottom of that by x plus 1. We're not doing anything to the right side. And notice again on the left side, I'm just multiplying. I'm just getting common denominators. I'm just multiplying top and bottom. So it's not like I'm multiplying the left side by x plus 1, and then I have to do it to the right side as well. Still didn't do it, but okay, so now I've got 2x minus 1 minus, you can think about that as being in brackets if you want to, minus 3 times x plus 1. I'm just trying to make sure that I do the numerator, the arithmetic correctly. So now I'm just going to simplify. So it looks like if we distribute, I guess I'll write it out. It looks like we would get a minus 3x. If we distribute, we would get a positive 3, but then that negative would make it into a negative 3. And if we keep simplifying, what is that? That looks like negative x minus 4 over x plus 1 greater than 0. Does that look good to all of you kind souls out there? I think it looks okay. So this is what we want. We want a single fraction, and then we want some type of inequality, less than, or equal to. I don't care. I'm using less than or equal to here. You want a single fraction, some sort of inequality, and you want 0. That is the goal. So that's usually going to be most of the work, honestly, I think. And now what we do is we set the numerator equal to 0. So just like I said, we'll set the numerator equal to 0, set the denominator equal to 0. I should write one more thing in my recipe, because then it turns into all those last problems. We just use test points. That's all we do. It just turns back into the other stuff. So negative x minus 4, let's set that equal to 0. X plus 1 equals 0. Let's use that. So it looks like the first one I could add x to both sides. That would give me negative 4 equals x. And I could subtract 1 from the second one. Those are my values. So negative 1. Whoops. Let's put negative 4 there. And how about we put negative 1 there? Okay. And again, now all I'm doing is I'm just looking at that inequality. And I'm thinking, notice if I plug negative, whoops. Okay, yes. Notice if I plug negative 4 in, I'm going to get 0 in the numerator, something non-zero in the denominator. I'm going to get 0, but 0 again is not greater than 0. So open circle at negative 4. Notice if I plug in negative 1, that's going to give me 0 in the denominator of my fraction. Right, if I plug in negative 1, I'm going to get 0 in the denominator. That's going to be undefined. Yeah, I agree, calculus. Maybe factoring the negative out is beneficial. I'm always like, to me, it's like one more step in a way, and people sometimes factor weird. So is it? I don't know. I agree with you. Personally, I would like to see it that way. So likewise, okay, so if we plug negative 1 in, you get 0 in the denominator. It's undefined. So that definitely can't work. And guess what? You just do the same thing, right? I've got an interval here. I've got 1, 2, 3 intervals. So for example, I could use x equals 0. I could test. So test x equals 0. And again, I'm just going back to that inequality. Notice if I plug in x equals 0, I'm going to get negative 4 on top. I would just be left with 1 in the denominator. Is that greater than 0, I ask myself. And I say, no, no way, Jose, because a negative number is not larger than 0. So I know that the stuff over here doesn't work. And again, you would do 2 more things. You could test something from that first interval. Again, I would probably pick negative 10 just because it tends to make the arithmetic easy. And I don't know, pick your favorite number. Whoops, I would pick maybe x equals negative 2. And just check. Okay. Fun stuff. Okay, it's quarter after. What's the next question we got here? Let me see how long it is. 25 is going to get a little long, but it is similar. And I'll let you all even look at this. So 25 I think is worth doing. So are 26 and 27. 28 and 29. 28 is nice. It's really an easier version of what we just did because we already have that good setup. We've got a single fraction and 0. 29 is going to be identical to 24 in the approach. So I will leave this to you. Do you want to do one more, or do you want to call it a day? So let's look at 25 here. I think it was 25. 25 is. I'm going to do my shameless plug here. One, I'll do I'll schedule a shindig for tomorrow so that you all know when exactly I'm going to do this. Give me a moment. If for some reason I'm late, like I said, bear with me. I will almost certainly be here on time. If there's a problem, I'll certainly post something either on the community or somewhere so that you know what's happening. Okay, let's do one more. One more. All right, that's the... oh, sorry, Queen Bee, you said call it. You've been outvoted. We'll go through this one faster. Same idea. The only thing that's trickier about this one, right, we have three terms. I've got 2 fractions on the left, 1 term, 2 term, and then one on the right, that's 3 terms. It's just going to make more of a mess. That's all that's going to happen. Same procedure. Let's make one side 0, so there's 1 over x, plus 2 over x minus 1. We'll subtract 4. We'll subtract 4 from both sides. We want to get common denominators. Okie dokie. So for my first fraction, I think we would have to multiply top and bottom by x minus 1. For my second fraction, I think we could multiply top and bottom by x. And for my third term on the left, I'm going to have to multiply both by x and x minus 1. And then, of course, we still have less than or equal to 0. Yeah, no problem, Ross. Oh, I forgot to do my shameless plug. My shameless plug is, one, please, if you're not a subscriber, please subscribe. You know, that's what we're supposed to say. I thought about making this like subs only. I was like, I'm not going to do that. The other thing is, hey, if you do want to help a brother out, you can go to Patreon. You can do donations through YouTube. They take so much. Don't do it. If you want to help a brother out, certainly no obligation whatsoever. You can go to Patreon. I think the lowest membership, you can do like $1 a month. So if you want to kick in $1 a month and buy your friend Patrick a cup of coffee after about half a year, that'd be awesome. So, but by all means, absolutely no obligation. Okay, let's do this bad boy. So, okay, I always like to do the denominator first because that makes me happy. I feel like I'm making progress. Okay, there's my common denominator on the left. So in the numerator, we've got x minus 1. If I distribute the 1, it's just x minus 1, so I'm going to drop the parentheses. We then have plus 2x, and then it looks like it's going to be minus 4x squared plus 4x, if my arithmetic looks correct there. So I'm going to keep simplifying the numerator. I'm going to do it in descending powers. So I've got negative 4x squared. So there's I used to write little dots over things. I'm like, okay, I've taken care of that term. I didn't like crossing them out because I had to go back and look at it for some reason. So positive 2x plus 2x, that's plus 6x. Okay, so I've got that one, and I've got that one. Oh, but there's another x. So that's actually going to be plus 7x. Plus 7x. And then we've got our minus 1. So we've got that part. And again, now I'm at my hurrah. I'm now at my hurrah step because I've got a single fraction on the left, a 0 on the right. We're in business. So now again, I do the same thing. I take the numerator, I set it equal to 0. I think yuck, because this is going to kind of be a nasty looking, well, whatever. It's a quadratic. I'll just use the quadratic formula. And then I set the denominator equal to 0. The denominator is easy because I'll just get x equals 0, and from that x minus 1, I'll get x equals 1, so there's 2 of them. And now I think, okay, I've got to find the solutions. Now, one little thing you could do here, and I certainly would, before I start using my A and my B and my C, yes, we're doing an inequality here. That's absolutely true. All I care about are the zeros. So to solve this, the first thing I would do is I would multiply both sides by a negative 1. The point being, you're still going to get the exact same zeros. That's all I'm trying to do. Find the zeros, Patrick. I can multiply by a negative. That doesn't change anything. This is not going to factor. So I would use the quadratic formula. X equals negative b. And again, I'm using my values here. So my a value is going to be positive 4. My b value is going to be positive 7. My c value is going to be positive 1. Notice if you didn't do this, if you used a equals negative 4, b equals negative 7, c equals negative 1, if we use these original ones, guess what happens? Well, again, you get the same zeros. It doesn't matter. Okay, so that's the point. But I'm going to use these. Again, the only reason I'm using is because they're all positive. Hopefully I won't make a sign mistake. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Yuck. So this is going to be kind of cruddy. Don't distract me, Ross. I'll start talking about that stuff. I gotta stay focused. So this is a -7 plus or minus. So what is that? 49 minus 16. 49 minus 16. That looks like that would be the square root of 33 all over 8. Holy moly, these are not nice numbers. That's okay. So now I've got -7 plus the square root of 33 over 8. And then I've also got, let me put my minus one there first. So I've got -7 minus the square root of 33. And then I've got -7 plus the square root of 33 over 8 as my other solution. I'm only half joking with you. Don't be sorry. It's an interesting question. Okay, so I've got now 1, 2, 3, 4 solutions. Again, I've done the exact same thing we've been doing. I made one side equal to 0. Hey, it's rational. I put them together. I set the top equal to 0. I set the bottom equal to 0. I've now got 2 new questions. These could be easy. These could be hard, depending on, what's on top and what's on the bottom. If the top's easy, it's easy. If the top's complicated, it's complicated, right? So now I've got these 4 solutions. You just do the same thing, number line. So there's 0 and 1. And you could put these in a calculator. Let's see. The square root of 33, the square root of 36 would be 6. So that's -7. What is that? -6. That's definitely going to be, so -7 minus the square root of 33 over 8. That should be over there. -7 plus the square root of 33, that's still going to be a negative number. Square root of 49 would be +7, so that's still too small, so it's still negative. So that would be -7 plus the square root of 33 over 8. My original inequality is less than or equal to, so this is a thing we should be careful about. The things that make the numerator equal to 0 are good, right? I can get 0 on top of a fraction. 0 divided by something non-zero is 0. And 0 is less than or equal to 0. So these two numbers would be shaded in. The -7 minus root 33 over 8 and the -7 plus root 33 over 8. Now notice the 0 and the 1. Either one of those values will make the denominator 0, which is going to make it undefined, which just messes everything up. It's not 0 if you have 0 in the bottom. It's undefined. So I know that this is an open circle, and this is an open circle. And now we're back at the same game. You're just taking, notice we've got 5 intervals now, right? 1, 2, 3, yeah. So I've got, because I found 4 points, you're always going to have one more. There's 1 interval, there's 2 intervals, there's 3 intervals, there's 4 intervals, there's 5 intervals. So again, you would have to take a test point. Maybe here you could use x equals 1/2. Here you could use x equals 10. And then figure out, what other numbers you should use. What is -7 plus the square root of 33 over 8? Maybe plug it into a calculator. But then you're just doing the same thing. Does it work or not? And again, we're just going back to, I would go back to the inequality where it's simplified or relatively simplified. So I would just start plugging those values back in there. Does it work? Yes or no? So, okay. I think that's it for me. I'm going to stay on for a couple seconds to see if people have any comments. I need to update my Patreon page too. I'm going to do that soon. Again, no obligation. What's it say? Tomorrow, what time's a good time tomorrow? What did we say? I don't know if you're still out there, Ms. Queen Bee. I think we said 6 o'clock. So how about 6 p.m. tomorrow? I think that should work. If not, I will try to post something ASAP. So we'll try to do this tomorrow too. We'll see what happens. And I'll keep grinding through the algebra. Yeah, does 6 p.m. work? Again, Central Time. I think we discussed we're both Central. Yeah, Apple, my pleasure. I hope that 5:30. Okay, let's change it. 5:30 works for me. Earlier is fine by me. I'm trying to catch people, you know, in all the time zones, but it's obviously impossible to do. Let's do 5:30. I actually do like that better. Meeting at 7. Fair enough. Okay, yeah, so let's do that tomorrow. So again, I appreciate it if you know anybody that may. Let me think about it, Ross. Um, I would actually, you know, probably just the Goldbach conjecture is kind of interesting. I would like to know if chess is a draw. Do you want to do 5? Let's do 5. That's even better. Okay. Last change. 5 p.m. tomorrow. I'll do the next session. If you know anybody that might be interested, teacher, tutor, student, friend, enemy, just let them know. I'd appreciate it. So, all right, my friends, it's Sunday. I hope you get a little bit of a chance to relax and um, decompress before the week starts. I hope everybody does have a good week. And yeah, I look forward to seeing y'all tomorrow. So have a good day, everybody, and I'll talk to you soon.